Welcome back, everyone. So in the last sections, we talked about how to find confidence intervals for a mean value, for when you have a sample mean, whether or not you know the population standard deviation. In this section, in the last section in this chapter, we're going to talk about how to find a confidence interval when you have a proportion. And now it is slightly different, but not much different, as you will see. So a lot of the things are still the same. And so it's not too much new, but we do need to talk about population proportions. And so remember that when we want to estimate something about a mean value, so let's say height, if we collect data on everyone, all of their heights will likely be different. But if we want to estimate something like a qualitative variable, a question like a category where somebody might answer yes or no, right? Then we would use a proportion. We want to know the proportion or the percentage that said yes to a particular question or that said no to a particular question. And so proportions are just like percentages. We just generally write them as decimals, and you want to use the decimals when you're doing the calculations. You can talk about them as as percentages, but you want to always use decimals when you're doing calculations. We use the symbol P to represent the proportion. And so, for example, if we asked a question on most surveys that you see, what percentage or what proportion of a company's customers are satisfied? You get satisfaction surveys all the time. So this is how you would estimate the answers to those questions. Okay. So let's talk a little bit about how to find a confidence interval for proportions. First of all, if you are going to estimate a proportion, you should have a simple random sample of whatever whatever you're estimating. So if you're asking people a question, you should have a simple random sample of people, essentially. The population that you are interested in should be at least 20 times larger than the sample. If you sample 15 out of 20 people, then this won't really work, right? If you sample 50 out of 100,000, then it'll probably be okay. You probably want to sample more than 50 in that case, but you want the population to be at least 20 times larger than the sample. If you sample most of the population, then you know most of the answer, and it's a little bit different. Or if the population is too small is the other problem. You should be able to divide the items into two distinct categories. You'll hear me refer to this as yes and no a bunch. But it doesn't have to be yes or no. It can be any two different categories, as you'll see in one of the examples in a little bit. But I like to use this because yes, no is a perfect example of the type of proportional question that you would answer here. And you need to have at least 10 responses in each one. So you need to have at least 10 yeses and 10 nos before you can even start to do that kind of thing. So let's take a look at the margin of error for a proportion. Okay, so just like with the other confidence intervals, we just need an estimate for the proportion, which we'll use from our sample, and then we need to find the margin of error. The difference between mean values and proportions is there's no standard deviation, right? Either you say yes or no, there's no standard deviation in that data, right? In qualitative data in that way. The variation is only yes or no. And so rather than using something like a standard deviation, or actually it's kind of like the standard deviation if you go back and look, okay, we're just going to calculate the margin of error using the proportions. Okay, the P with the little hat over it represents the sample proportion, and Q with the little hat over it represents the complement. Okay, it's just 1 minus P. So this is the same thing as the Z critical value. Okay, notice we're going to use the Z distribution again in this case as well. That'll make things a little bit easier. This is the same thing as P times 1 minus P over N. Once again, this should look very similar to the project that you did a couple of weeks ago, where you dealt with a sample proportion, because you did something very, very similar. So remember that when we want to find the sample proportion and the complement, if we say that X is the people who said yes, then we can calculate the sample proportion by taking the number of yeses divided by the total. And we can do the same thing for the number of no's divided by the total. 85 divided by 126, 0.675. And so we can find Q then in a few different ways. We can say it's 1 minus P, which is just 1 minus 0.675, or 0.325. And so we have Q this way. And we can also figure out if this many people said yes, well, we can figure out how many said no by just subtracting there. 126 minus 85, that means 41 said no. And then we could find Q that way. 41 over 126 is going to give us the same thing we got before, 0.325. Either way works. We now use these proportions to find the margin of error. So let's look at another example. A recent poll of 149 participants found that 73 reported their favorite Joker was Heath Ledger. Calculated 90% confidence interval, and then we're going to round the proportions to 3 decimal places. So if we want to know how many said yes, how many said Heath Ledger was their favorite, well, that's 73 out of 149. And so that's going to give us 0.490, which means those who said no would be 0.510, 1 minus. Our sample size in this case is 149. We need the critical value for Z values when we're dealing with proportions. It's much easier, right? We can still use this table. The critical value for Z for a 90% confidence interval, 1.65. And so the margin of error, 1.65 times the square root of 0.490, 0.510 divided by 149. Now, it's important how you do this in the calculator. Make sure you do everything under the square root first before you take the square root. So 0.49 times 0.51 divided by 149. That's going to give us, I've run out of a little bit of space here. What we have is 1.65 times the square root of 0.01677. Now, when you take the square root of a decimal number, it gets bigger. So this is 1.65 times 0.0409. And now I'm completely out of space, but I'm going to write the margin of error over here. Oops, 1.65. And we get a margin of error of 0.06. We'll just call it 0.068. And so our best estimate for the proportion based on what we have here is 0.490. To find the upper limit of the confidence interval, we just add 0.490 plus 0.068, 0.558, and then subtract 0.490 minus 0.068, 0.422. So we could estimate that we could be 90% confident that between 42% and 55.8% of participants reported that Heath Ledger was their favorite Joker. And so it's very similar to all the other problems that we've done. The only difference is how you calculate the margin of error. The interpretation is the same. You just have to find the proportions in the data and then use that as essentially the variance component of your margin of error, as opposed to using the standard deviation. It's actually related to the standard deviation that you calculated when you had proportional data, or data where you were calculating proportions. Let's look at some more examples. So we have a random sample of 300 graduating high school seniors, and it's found that 195 of them had taken the SAT. We want to estimate a 95% confidence interval to determine the true proportion of high school graduates that took the SAT. So to do that, we're going to need our sample proportion, 195 divided by 300, 0.65, which means the complement, 1 minus p, 0.35. We need our critical Z value, okay, for a 95% confidence interval. It's going to be 1.96. Okay, and we need a sample size of 300. To find the margin of error, we're going to multiply the critical Z value times the square root of p times q over n. So 1.96 times the square root of 0.65, 0.35 divided by 300. And again, remember to do the thing underneath the square root first. 0.00758. I'm just not rounding here. I just want you guys to kind of see the intermediate steps so that you can make sure you're getting the right numbers in your calculator. And then when we multiply that times each other, we get a margin of error of 0.054. And we can write these to 3 decimal places. And so for our 95% confidence interval, 0.650 minus 0.054, boundary is going to be 0.596, 0.650 plus 0.054. So we can be 95% confident that the true proportion of high school graduates who take the SAT is between 59.6% and 70.4%. So 95% confident, somewhere between 60 and 70%. Let's look at another example. A survey on student loan debt collected from 1,404 students found 23% paid for their education with student loans. Let's calculate the margin of error and essentially the confidence interval. I left out a piece here. Let's do a 95% confidence interval. And so that's going to be, again, 1.96. 23% said yes, paid for their education with loans, which means 77 said no. Our sample size is 1,404. I'm going to do this one without the intermediate steps. we get a margin of error of 0.022, okay, or what is essentially plus or minus 2.2%. Okay, so if we know that the survey told us 23% paid for their loans, paid for their education with loans, okay, our margin of error is plus or minus 2.2%. Okay, so that means we would essentially add 2.2% to that. And so it'd be somewhere between 20.8% and 25.2% would be the true proportion of students who paid for their education with student loans, right? And so that's what you see in the next slide. We can be 95% confident that somewhere between 20.8% and 25.2%. Okay, we don't know where that number is. Okay, it could be closer to, the true value could be close to 20.8. It could be close to 25.2, right? It might be in the 5% that we don't see, right? That's outside of this range. But we can be 95% sure that it's between these two values. Let's look at another example. This is one question that I like to use from the survey when we talk about confidence intervals for proportions. So what proportion of community college students use an iPhone? Here we have 32 said yes, 9 said no, and our sample size. If we want a 90% confidence interval, let's just go back real quick and look at this. 90% is 1.65. So our critical Z value, 1.65. Our sample proportion, 32 out of 41, or 0.780. Okay, the complement then is 0.220. There are 9 divided by 41. To find the margin of error, 1.65 times the square root of 0.78 times 0.22 divided by the sample size is 41. Now 0.78 times 0.22 divided by 41, and then take the square root. 1.65 times 0.06, 469. 4, if you then multiply these two, 10, we'll just call it 107. Okay, so in this case, the margin of error plus or minus 10.7%. And part of the problem there is we have a really small sample. In general, when you see these questions with proportions, you'll see much larger samples because you need a larger sample to reduce the margin of error. And so now if we want the confidence interval, we have our proportion plus or minus the margin of error. So 0.780 plus 0.107, 0.887. If we subtract 673, and so we can be 90% confident that the true value of, or that the true proportion of community college students who use an iPhone is between 0.673 and 0.887, or 67.3%, 88.7%. As I mentioned here, one of the issues here with the margin of error being so large, right, plus or minus 10%, is that the sample size is small, right? And you notice that we were able to calculate the sample size for the required sample size for means when we wanted a certain margin of error for our mean values, right? We can do the same thing with proportions. We can calculate the sample size we would need for the proportional values. And it's exactly the same type of calculation. Okay, but the equation is just a little bit different because we've got to use P and Q again, as opposed to using the standard deviation. And so that's the only real difference here. Okay, and just remember here, the margin of error should be written as a decimal, not as a percent. Okay, so a federal report indicated that 27% of children aged 2 to 5 had a good diet. What's the minimum sample size needed to estimate the true proportion of children with good diets within a margin of error of 2%? Okay, so our margin of error, 2%, okay, that is 0.02. We didn't get a critical Z value here. Sometimes the book won't give it to you. I think this one does in general, but we're going to use a value of 2 here. I think there's another example where the Z is given to us. Now, it says 27% have a good diet, so that's what we're interested in here. That means that 73% say they don't have a good diet. Now, if we want to calculate the sample size, 0.27, 0.73 times 2 divided by 0.02 squared. When we multiply all of that, we need a sample size of 1,971 in order to get a margin of error of 2% or less. Then we do a very similar thing here. According to a recent survey of U.S. homeowners, 25% said they have a direct satellite receiver. Assuming the percentage remains the same, how many more homeowners to be surveyed to have a margin of error of 3%? Okay, so if we want a margin of error of 3%, that's 0.03. Again, our critical Z value here, we can just use as 2. Okay, this is because there's no confidence level listed here. So we that's what you see here. Point that out really quickly while I go back to the other thing. Okay, this is 0.25, 0.75, 25%, 75%, 2 divided by 0.03 squared. Okay, so again, remember to do the exponents part first. So 2 divided by 0.03, square that value, then multiply times the two decimals, 0.25 times 0.75, 833.33, which means you need a total of 834 in order to have a margin of error of 3%. Okay, they already surveyed 378. How many more is what it asks. So then you just 834 minus 378. How many more people do we have to talk to? We need to survey 456 more. And then the margin of error will drop below 3%. Let's look at one more example here because there may be some in your homework this week. If we have a really small sample, then we can use what's called the small sample method. And what this is going to do is just adjust the proportions just a little bit and the values just a little bit so that we can use these use the same distribution while making our estimate a little bit better. And a simple random sample of 15 seniors, 8 of them had found jobs. Okay, we want to use the small sample method to construct a 90% confidence interval for the proportion that found jobs. Okay, so here, our adjusted proportion, we're just going to add 2 to the numerator, add 4 to the denominator. Okay, and so that's what the little tilde thing over it is the adjusted proportion. And that's going to be 8 plus 2, 15 plus 4, that's 10 over 19, 0.526. Okay, so 1 minus that, 0.474. And again, if we go back and look to find the confidence interval, the only difference is now P, our new proportion, times Q divided by n plus 4. And then we take the square root. So for a 90% confidence interval, the critical Z value, 1.65. And so to find the margin of error, that's going to be 1.65 times the square root of 0.526474. Okay, divided by the sample size plus 4, so divided by 19. 0.526 times 0.474 divided by 19, and then take the square root. That is 1.65 times 0.11455. So the margin of error is 0.189, plus or minus 18.9%. And that small sample is a bit of a problem there. But then we can use our proportion and our margin of error, right? We could even probably write these little things over them if we wanted to. And so if we add the 2.526 plus 0.189, 0.526 minus 0.189, 715. And so our confidence interval, is going to be 0.337, 0.715, or between 33.7% and 71.5% of the seniors at the college, we can be 90% confident, found jobs. Right? That is not a great estimate, but it tells us something. As you work through the problems and review for your test this week, don't forget to review the questions about the standard deviation when the means are known. When the standard deviation is known and unknown, and all of the things we did in chapter 6. Next week, we will talk about hypothesis testing, and I'll show you again that you've kind of already learned it. Just have a great week, and I will see you guys next time.